Okay, so what we want to do now is applications. Applications. Where do we use definite integrals? So let's enumerate them and start from 0. The first application that we had was just, you have A, and you have B, and you have a function, and you want to know the area under the graph. That was actually the motivating application that we had. So the area under the graph of f between A and B, this is f. So this was the 0th application. With this we started. Okay? So number 1 would be just something in the epsilon neighborhood of number 0. Namely, suppose you have two functions, A and B, and you have two functions, f and g. Let's say f is something like this, and let's say you have another function, g, which is something like this. So this is g in orange and f in blue. And what you're interested in now is not the area under the graph, but the area trapped between the graphs. Okay, so we somehow want to mention or to encode or to find or whatever this area. And it's of course going to be expressed in terms of an integral. And if you think for a minute, there's nothing really too complicated going on. So over here in this region, it's the area under the blue function minus the area under the orange function. Do you agree? Then in this region here, they switch roles. So I have to take the area under the orange function minus the area under the blue function. Does everybody agree? Can you see it? So all in all, what I get is that the area trapped between the graph, let's call it S, equals the integral from A to B. And what I want is the integral of the difference between the two functions. But I don't really care which one's bigger. I want it in absolute value. Okay? So what I get is the integral of f of x minus g of x in absolute value dx. So this is the area between the graphs. Clear? Okay. There are many applications within mathematics that seem kind of surprising. One can use Riemann sums to calculate limits of sequences. That's something really surprising. I don't want to spend time on it here. Maybe you'll see examples of that in homework or in your tutorials. What I want to show you is another example of an application within mathematics that's more intriguing a bit, or maybe surprising even. So suppose we want to find not the area under the graph, and not any variation of that. Suppose we want to find the length of a graph. I want to know how long is this line. Okay? And one way to do it is to take a string, take a piece of string, carefully put it on the graph, very carefully. Now it's laid on the graph. Do you see it? It's blue. Then you pick it up, do toing, and then put it on a ruler. Do you agree that would work? Yup. But for that, you need to be able to draw the graph very accurately, if you want to use that method, and you need to have a string. Okay, you may be able to pull out one of your hairs and do it, but I would be in trouble. Okay, so we want to do this mathematically, and the idea is the following. So what we're going to do is, Here's A, here's B, and we want the length of the curve, not the area under the graph, the length of the curve. So we're going to do a partition of the interval AB. Here's a partition, just any partition. And then we're going to calculate the values of the function on the x's which we get from the partition. There they are. And then we're going to take secant lines connecting these. So I'm going to get this secant line, and then this secant line, and then this, and then this. So this broken orange line, well, it's easier to calculate its lengths because it's just a bunch of straight line segments, right? Are they the same as the length of the blue line, which is what I was looking for? No. Are they close to it? Yes, they're an approximation. The sum of the lengths of the blue secant of the orange secant lines is close to the length of the blue line. How close? Well, you can see here that not too accurately. How can I make it better? Right. More partitions, or a more delicate partition, and we used the term, what was the term we used? No. Oh, I'm missing a word. Not shrink. Oh, I'm missing a word. Anyway, so we can make the more smaller segments, refine. We can refine the partition. That's the term we used. And for example, I can add maybe another one here, and then this would go away, and then I would have, instead of it, two segments like this, two secants, and now my approximation is better. Do you agree? So let's see what we have. So I'm going to make a zoom in on just this first segment here. Make a big zoom in because I want to draw on it many things. So here's a huge zoom in just on the first segment. Okay? Or on any segment. So let's call this one xi minus 1, and this one is xi. These are 2 points in the partition, any 2 points. And here's the function itself. That's the function itself just on that subinterval. And here's the secant line, which I get by taking the values at these 2 points. Okay? And so what is this point? What are these 2 points? This is the point xi, f of xi. And this is the point xi minus 1, f of xi minus 1. Do you agree? And if I'm going to call the length of the orange one, I'm going to call it Li, L sub I, L for length, L sub I. And I'm going to add to this drawing just one more line. I'm going to construct the right triangle here by taking the equal value here. Okay? So what do I get? I can do a Pythagoras argument on this right triangle, and Li squared is this squared, which is just the difference in the x's, plus this squared, which is the difference in the f of x's, square root. Do you agree? So by Pythagoras in this triangle, I get that Li equals the root of xi minus 1 squared plus f of xi minus f of xi minus 1 squared. Does everybody agree? So the total length of the broken orange line would be the sum of these as I ranges from 1 to n. Is everybody with me? Questions? Good? Okay. Now, look at this expression a second, and in particular, look at this thing. What I want to do, remember we said that there's this Lagrange theorem, the mean value theorem of Lagrange, which shows up where it's least expected. Remember we said that? Do you expect it now? Well, now you do because I told you to expect it. But suppose you don't expect it. Now it's going to show up when it's least expected. So here it goes. By Lagrange, there exists a CI between xi and xi minus 1 such that f prime at ci equals f at xi minus f at xi minus 1 divided by xi minus xi minus 1. Do you agree that this is precisely Lagrange's theorem applied on the interval xi minus 1 to xi? Do you agree? Now, note that in order to say this, in order to do this, I have to require f to be differentiable on this interval. Okay, I'm doing Lagrange. So we're going to assume here that f is differentiable. And of course, continuous. Okay, so we have this. And from this it follows that this difference equals f prime at ci times xi minus xi minus 1. Do you agree? And I'm going to substitute this term here with the product of f prime ci times xi minus xi minus 1. So let's write that. So this thing now equals, so by this, I'm sorry it's a bit messy, but I want to keep it all on one board so you don't have to bounce back and forth. So what I get is the root xi minus 1 squared, xi minus xi minus 1 squared. That's this. Plus, and now instead of this, I'm going to write f prime at some intermediate point ci times xi minus xi minus 1, and all of this squared. And everything inside the root. Did everybody follow? Questions? Good? Okay. Now I can pull this xi minus 1 squared. It's a common factor in both of these. I can pull it out, take it, it's squared and rooted, so I can pull it entirely out of the root. So now we can continue on this board. I get xi minus 1 times the root of 1 plus f prime at ci squared. So this is one little orange segment. This is one Li. And therefore, the sum of the Li's, I equals 1 to n, which is the length of the broken orange line, which is our approximation, equals the sum, I equals 1 to n, of these things. So I'm going to write it root 1 plus f prime ci squared times this thing. But what is this thing? Give me a different name for this, which we've used previously. Delta xi. Very good. Good. Right. This looks peculiarly Riemannish. Oof. Sorry. Do you agree that this reminds us of a Riemann sum? There's the delta xi's, there's the sum, I equals 1 to n, For it to be a Riemann sum, what would we expect to see here? Just f of ci, right? A Riemann sum was sum f of ci delta xi. Remember those were the Riemann sums? Here we don't have f of ci, we have 1 plus f prime of ci squared root of that. No, that is a function. This thing, so let me write this. This is a Riemann sum. But not of f. The Riemann sum corresponding to f would be just having here f of ci. That's it. But then this Riemann sum would actually give the area under the graph. That's not the problem we're trying to solve. This is a Riemann sum of the function root of 1 plus f prime of x squared. This is the Riemann sum corresponding to this function. Root of 1 plus f prime of x squared. And when we refine the partitions, make the norm smaller, take the subintervals to be smaller and smaller, these sums converge to the length of the curve, right? But what do these sums converge to in terms of the mathematical theory? As we take the delta xi smaller, they converge to, and this is the bottom line of this thing, L, which is the length of the curve, the limit of the broken curves, equals the integral from a to b, not of f of x dx, but of this thing, root 1 plus f prime of x squared dx. Okay, so this is called the formula for curve length. It can be extended to very general things. And you'll see that in your next course, in Calculus 2. It can be extended to curves. So this is called curve length formula. It's a very special case of it, where the curve is not just any curve, it's a graph of a differentiable function in one variable. This is a very special case. In Calculus 2, which is coming rather soon, you're going to see how to extend this to a length of a curve in 3 space, okay, which is not necessarily a graph of a function and not one-dimensional, and still there's a very similar formula whose special case is going to be this. And then you're going to say, hey, we saw this, I remember this. And you're going to see how it reduces to this for the special case where the curve is the graph of a function in one variable. Yes?
How can we just replace the ci with x?
That was the whole idea of Riemann sums. At the limit, the Riemann sums converge to the integral. The Riemann sums were f of ci delta xi, they converge to the integral of f of x dx. When it's not f of ci, but this thing, call it g of x, evaluated at the ci's, they converge to the integral of g of x. Okay? Let's do an example. Example. Let's find the length of a circle. What do I mean, the length of a circle? Where a circle is not a graph of a function, right? A circle is not a graph of a function. Do you agree? But what I can do is take half a circle. Now it is the graph of a function. Suppose this is 1 and this is minus 1. What's the function here? It's a circle of radius 1.
X squared plus y squared equals 1.
Right. X squared plus y squared equals 1 is the circle itself, but that's not a graph of a function. What's just this upper semicircle? Right. This is the function root of 1 minus x squared. Do you agree? On the interval -1, 1. If I find the length of this graph, multiply it by 2. That's the length of the curve, which is the circle. Do you agree? Everybody? Okay, what's the answer we're expecting? Pi, right? Because the whole thing is 2 pi times the radius, which is 1. So 1/2 of it has to be pi. We're expecting to get pi. Do you agree? So this is going to be our f of x. So f of x is root 1 minus x squared. F prime of x, remember, we need f prime in order to plug it into that formula. So what's f prime? The root of something is 1. So this is 1 minus x squared to the -1. The derivative is -1 times the thing to the -2. So that just sends it to the denominator. And then I have, sorry. This is 1 minus x squared to the power 1/2. The derivative is 1/2. This to the power -1/2, which sends it to the denominator. But then there's the inner derivative, which is what? Minus 2x. This is f prime. And then the 2's cancel, so I just get minus x divided by root 1 minus x squared. This is f prime. Good? And now I want to find root of 1 plus f prime squared. This is the expression I have in that formula, which we just derived. So I'm going to plug this into here. So I get the root. So this is our side calculation. And this is what I'm plugging into here. So I get the root of 1 plus f prime squared is this squared. So I get x squared divided by 1 minus x squared. Following? Good? Nod your heads. Questions? Okay, good, good. So what do I get? I get, let's do a common denominator. So I have 1 minus x squared plus x squared, so it's just 1, divided by 1 minus x squared, and the root of that. Or I can even write it, let's write it, better yet, let's write it as 1 over the root. Good. And now the length, L, which is the length of the half circle, is the integral from -1 to 1. Those are the endpoints of the interval of this thing, of the root of 1 plus f prime x squared. So I get 1 over the root 1 minus x squared dx. And do you recognize this is a derivative of something? It's an immediate one. Right, it's arcsine. So it's arcsine x evaluated between -1 and 1. What did I just use? Newton-Leibniz, right? Antiderivative evaluated between the endpoints. What's arcsine of 1? It's a number whose sign is 1. So it's pi over 2 minus, what's arcsine of -1? Minus pi over 2. You can't say 3 pi over 2, because remember what the domain of arcsine is. You have to restrict to the domain of arcsine. So it's this, and this equals pi, as we hoped to get. Good? So this is very naive. This is very, it's a very particular case. It's kind of a promo to things you're going to do in Calculus 2 in a much more general context. it's going to be fun, and that's not a joke. The reason it's going to be fun is that everything we do here, in fact, everything we're doing here, the drawings are very boring. The drawings are always one-dimensional, right? There's just the XY coordinate system and the graph. You can't go too wild with that. I mean, we're so excited every time we have the opportunity to draw the Dirichlet function, right? But that's as far as fun can go. In Calculus 2, we're going to have curves in space. Try drawing that. We can have 4-dimensional or 5-dimensional curves. Those we're not even going to be able to draw, but we're going to have to somehow imagine them, right? And we're going to have functions of 2 variables whose graphs are like these blankets hanging in the air. Okay? It's going to be fun.
Are you going to be our professor?
Irrelevant. Okay. Good. So all of this discussion was application number 2, and it's still in the realm of pure mathematics. What I want to show you now is really briefly, some applications, for example, to physics, and we're not going to have time to discuss them with too much detail. I hope that when you eventually learn physics, are you already learning physics so you've probably seen many of these things. Good. Okay, so this would be number 3. So, for example, suppose you have a wire with mass density given by rho. That's the letter usually used. And in fact, you can replace this with, instead of mass density, you can do charge density. I'm guessing that if you're taking physics 1, you're discussing, you're not doing electromagnetism yet, right? That would probably be in physics 2. Okay, but do you know what mass density means? Okay, and so we have a wire with mass density rho, but the idea is that it's rho of x. It's changing. It's not a fixed density. It's a function of x. Okay, so it's a different density at each x you look at. So think of a wire made of different materials at different places, so the mass density varies. Okay? And you want to know what is the density. So what's the density, what's the mass? So mass density rho, find the mass of the wire. So if the mass density is fixed, what is the mass?
Volume times density.
Right, the volume times the density. We're going to do everything one-dimensional. Our hands are tied. One-dimensional in this course. So it's not going to be volume, it's going to be the length. Okay, it's going to be a one-dimensional wire. Okay, one-dimensional wire, the x-axis if you want. You can think of it as just the x-axis. So if rho was constant, then the mass would be rho times delta x, times the length of the wire. Do you agree? Yep? If it is, this is if, but it's not. It's rho of x. It's varying. So what do we do? What do? We take our wire.
So we have m of x, we have a function.
No. We have a wire. We want to know its mass. The mass of the wire is not going to depend on where you look at. It's the mass of the entire thing. Okay? The density of the mass varies, but the mass of the entire thing is a number. Okay? So what's that number going to be? And I'm going to really wave this, but just so you pick up the idea. You're going to say, okay, look at the wire, break it into small little wires, and assume that on each of these small little segments, rho is fixed. Approximate rho by its value at the midpoint, or whatever. What are you going to get? You're going to get a Riemann sum. Okay, so when rho of x is not constant, it can be any function, we approximate by taking little segments and on each one assuming that it's fixed. So we get some rho of some point in that segment, Ci, times delta xi. Is the idea clear? And as we refine, what do we get in the limit? And this is how I assume you've been calculating masses when you know mass densities. M equals the integral from A to B, where A to B are the endpoints of the wire, of rho of x dx. And likewise, if it's charge density and you want to know the charge of the wire, then you'd call it Q, and it would be the integral of rho of x dx. Clear? Have you encountered these things already? Okay. But is the idea clear? Is the idea clear? Okay. Another instance where something very similar would occur, for example, I'm really just touching on these applications, and maybe you'll have some examples in homework, but really this is just to give you the flavor, and the real taste you will see when you actually use them, and you're gonna. Okay, so maybe another example. Suppose you have so you know that the work done by a force is given by the force times the distance on which it operates, right? Do you all know this? So this is work. Work. Have to work. Force. May the force be with you. Do you all know this? Okay? But what if the force is not fixed? What if I'm trying to move this table here and I'm not... I had breakfast, I'm strong, and then I get tired, and I move slow, and then I move. Okay, the force is not fixed. The force can be a function of x. So if f of x is not constant, then just like before, I would break the distance along which I am applying this force into little distances, assume the force is constant on each little distance, so I would get a sum of f at ci times delta xi's, and in the limit, so then in the limit we will get that the total work done, which is still a number, is given by the integral from a to b f of x dx. The work is the integral of the force. Okay? Have you seen this? Oh, good. Okay. Now, so again, this is really a crash course on applications. I'm not going to have time to go further into details. You will see some examples. But I do want to mention something important that stems from these examples, and that's how you should think of integrals. And that's important. And the idea is the following. We think of integrals as, what are they? They're sums. They're Riemann sums that we refined. Okay, so we kind of are not summing, instead of summing 10 terms, we're summing 100 terms. No. We're summing 1,000 terms. Nah, we're summing 1,000,000 terms. Nah, we're summing kind of continuously. Do you see that? That an integral is kind of a continuous sum. Do you get that feeling from here? I mean, what was this thing? This thing was, we took the sum, so W, okay, so the sum of f evaluated at some little points times these little intervals, That was the approximation, and this converges as n goes to infinity to the integral, which is the actual work. This is kind of what happened here. Same thing for the previous example. So this is really a continuous sum. So let me write this. We think of this definite integral as a continuous sum. And if you keep that in mind, many various kinds of integrals which we're going to encounter in the next course, when we do surface integrals and line integrals and whatnot, if you think of them like this, they're going to be easy to absorb. And in particular in many, many applications. And moreover, the notation, I think I mentioned this, the notation snake was invented by Leibniz, is due to Leibniz. This guy was smart. Is due to Leibniz. I think I even found that it was invented in 1675, but I'm not entirely sure of this. And it comes from a letter that is now extinct, which is this long esting. Okay? And I think I read that it still can be found in old writings. For example, in the Constitution of the United States, you can find these long S's appearing somewhere. And it's just a form of a long S coming from the word summa, which means sum. Okay? So intuitively, these integrals are continuous sums, and that's where they come from. And that's really the role they're playing, and that's how we should think of them. The fact that the notation is shared by antiderivatives, that's a totally different story. That's only because of the fundamental theorem. Okay, I mean, we discussed it, but this is really the idea of summing these rectangles continuously. Okay, or summing the force continuously to get the work. Okay? Okay, so what we're going to do next time is still work on integrals, but take it one step further and try to see if we can remove the assumptions that the function is necessarily bounded and that the interval is necessarily bounded. What happens when we allow unbounded functions and maybe intervals from a to infinity? And those things do exist, we just have to define them carefully, and we'll do that next time.